in this lesson we're going to continue looking at the cracking of alkanes. In particular, we're going to look at this typical laboratory classroom experiment. Okay, so let's just label the apparatus for us. We've got a boiling tube. A boiling tube is a test tube that's able to undergo very high temperatures, typically made out of Pyrex. And in the boiling tube we've got some mineral wool which has been soaked in paraffin. And to assist in the cracking process we're going to use a catalyst, and in this case we're going to use porcelain chips. You remember in the industrial cracking of alkanes in the refineries, the catalysts that are used are alumina or silica. Well, these porcelain chips do the same job in the laboratory. Okay, so these act as a catalyst. Okay, you'll notice that the test tube is inclined at an angle. You'll see the reason for that in a minute. Now, in order to get the cracking process going, we're going to have to heat the mineral wool, and we're going to have to heat the porcelain chips, the catalyst, at the same time. So what we do is we start heating the porcelain chips, and these need to be round about a temperature of 500 600 degrees Celsius. So we need to heat those until they get really hot, and then we're going to move over to the mineral wool soaked in paraffin, heat that for a little bit, perhaps 2 or 3 seconds, move back to the porcelain chips, heat that for another 10 seconds. We've got to keep those hot. Then back to the paraffin, heat that for 2 or 3 seconds, and back to the porcelain chips, and just keep going backwards and forwards between the two. And so what's going to happen is the paraffin is going to evaporate, pass over the porcelain chips, and it's that point that the cracking process is going to take place. So the long-chained alkane molecules in the paraffin are going to be cracked. They're going to be broken down into smaller short-chained molecules, which will be liquids. Okay, and those liquids are going to gather here just before the stopper in the test tube. And the other products in the cracking process are going to be alkene gases, which are going to pass down this tube, and they're going to be collected over water. Okay, so we're going to get alkenes collecting over water, and this test tube is gradually going to fill. Alkenes, ethene typically, and propene. So once this test tube is filled, we'll put a rubber stopper on it. Okay, and we'll add just a few drops of bromine water, and then we'll shake the test tube, and the bromine water will change colour from this light orange colour to clear, which will indicate the presence of the carbon-carbon double bonds in the alkene molecules that are present in the test tube. So just to summarise again, what we're doing is we're cracking the long chain molecules present in paraffin into shorter chained alkane molecules which collect, these are liquids which collect inside the test tube, and then also alkene gases which are delivered through this delivery tube into the test tube. They collect in the test tube, and then they're tested with bromine water to demonstrate the presence of the carbon-carbon double bond. Let's just have a look at the chemistry a little bit more closely. Now, substances like paraffin are usually made of a number of different alkanes. That's to say, alkanes with different chain lengths, and typically they're a little bit longer than this. Around about 15 carbons is typical for kerosene paraffin, but they may also contain shorter alkane molecules, for example, such as dodecane, which is 12 carbons. So we're going to use dodecane because it's physically smaller and easier to get onto the page. So we'll duplicate that, and in the cracking process, let's just say that the molecule is cracked here, right? So the cracking occurs. That leaves us with an unpaired electron here and an unpaired electron here. And so what's going to happen is this unpaired electron is going to come down here, and this unpaired electron is going to grab hold of the hydrogen atom here to form an alkane, in this case octane, and the unpaired electron that is left from this bond will join on with this unpaired electron to form a carbon-carbon double bond. There. Okay. And so what we're left with now is a new shorter chained alkane, which is decane and ethene. Now what I'd like to emphasize is that this cracking process doesn't just produce one alkane and one alkene. As I mentioned earlier, you're going to get a number of different shorter chained alkanes collecting here and a number of different alkenes in the test tube. There, label that. And so what might happen now is that this decane molecule will itself get cracked. This time it gets cracked here. Alright, there. And so the same process happens. You get an unpaired electron here, an unpaired electron here. This unpaired electron goes to form a double bond, while this unpaired electron grabs hold of the hydrogen here to form a new alkane called heptane with 7 carbons in the chain, and then the unpaired electron left behind joins with this unpaired electron to form a double bond, leaving us with heptane. That's the 7 carbons in the chain, and propene. So it's all looking a bit complicated, but this isn't quite as horrendous as it looks. Let's just remind ourselves what happened. We started off with dodecane, that got cracked into decane and ethene. Okay, so we've got an ethene molecule which will move down here. Then the decane was cracked here into heptane and propene. So we'll move the heptane and propane down here. Right, so we started off with dodecane C12H26. That represents our paraffin or kerosene, and that was cracked into heptane, which is C7, and then H16, and into 2 alkenes, which was propene C3H6 and ethene C2H4. So if you do your sums, you'll see that the carbons and the hydrogens all add up in our equation below.